I'm Steve Guo. I'm going to talk about patterns and anomalies of loss development in P&C insurance market. So first of all, thank Mike for organizing this amazing conference and workshop. So I was here during the first summit during in 2019 while I was working as a visiting assistant professor here. It was a great full day event, learned a lot of the topic, and got to know the then speaker author, and later it develops into our collaborations. And thanks Ledger Investing for willing to provide the data. So in my talk, you'll find a similar triangle data that will be mentioned. And the topic is not, eventually I'll be speaking a little bit about our loss reserving models, but most of the talk will be based on how we get to our models. And a lot will be based on the exploration on the loss triangle data. So as Ron and Mark have already gave extensive introduction to the topic of the loss reserving and loss triangles, so I'll keep my introduction to the shortest as possible. So I'm also dealing with the P&C loss triangles. And as we all know, like liability lines, like workers' compensation, has 10+ years of loss development. And that results in the data with reporting delay. So our main interest is with any functional data with reporting delay. So as Ron and Mark have shown you, I'm going to show you again one example, loss triangle here. So we also care about the loss development over the accident year. So as a function of the development lag, in this case for statutory triangles, we have 10 lags. So for we could also have like quarterly triangles that we have more discrete observations over. Now, of course, we want to predict the lower right-hand side of the triangle, which is unknown. But in our research, in our study, we also care about what happens before the top row we have seen here. So for example, between the year 1980 to 1999, they are already, in these years, the laws have already finished their development. We'll have full loss development curves for all the previous years. So what we do, we try to do some exploration on the historical information and see if those historical information can help us, can give us information and help us to do the loss reserving. Let's go back. Sorry. And briefly mention some related case. So the functional data with reporting delay. So the P&C loss triangle is one main example. The other example might be in the medical case reporting. That's because when there's a delay between the symptoms onset of the symptoms and reporting cases. So actually, the symptoms that's happening at the same time is being reported in the delayed lag, for example. The AIDS cases, so we can see a similar pattern here. We can see all the cases before the 1990 almost finished reporting, but after the 1991, it's incomplete. So face the same problem, try to project the incomplete curves. And you can also study the complete information. But we'll be focused on the P&C loss triangles. And sort of a reason, I think Ron and Mark have given a really extensive introduction on that. But our focus here is on, we have a bunch of triangles, namely industry-wide, across many, many years and across many companies as well. So the regulators, the reinsurers, and the insurance ILS, security investors might be interested on an industry-wide loss development or the loss ratio development. Right? Might be interested in studying the pattern of the loss development over a business line. So looking at the curve across each accident year. On top of that, looking for any anonymous loss development for particular insurance. So among these thousands of the loss development curves, is there anything that is out of the normal in terms of shape or the magnitude? So we'd be interested in looking at. And all that will help the interested party to decide to increase or reduce exposure in particular business line or type of the company. Right. Then while we gained the information by studying the historical loss development and industry-wide loss development, that maybe can give additional information into the loss reserving topics. So we're looking at possibility of loss reserving beyond a single triangle. So can the historical pattern of the loss development inform something about the future? And can the loss development from other similar insurers provide additional information for the loss reserving purpose? Right. So our research has two parts. The majority of the talk today, we will be talking about the first part, is that using the statistical learning approaches, we can explore around the loss development curves. In terms of what's the general pattern of the loss development, for example, what's the level of the magnitude of the incremental loss ratio across the years and across different companies? And how is the loss development curves linked to the company features? For example, is there a particular kind of companies? For example, this stock company versus the mutual companies, do they have a different patterns of the loss development? Or like Mark just has mentioned, if for the company that has different capitalizations or the size of the business, so does the loss development varies? And we use unsupervised learning to discover the pattern and anomalies of the industry-wide loss development in terms of the functional curve over the accident year, so as a function of the development lags. And the first study actually propels our thoughts in developing a loss reserving model. So in the end, I'll briefly mention the ideas of our loss reserving approaches. So indeed, in terms of the functional curves, how do we forecast the incomplete loss development curves? Right? In short, we will use a non-parametric data-driven procedure to forecast the future losses by matching the partial loss development experience against a similar completed pattern in a database. So you'll see we'll take advantage of the information of the already completed loss development and also with the complete loss development in the history. Right, let's go into the data. We mainly look at the paid loss triangle data. And for the workers' compensation business, and we obtain two variables, very familiar variables, incremental loss ratios, divide the incremental paid loss in each of the development lags over the net premium earned. So by normalizing that across the company and across the development years. So we get comparable results between each observations. And later, cumulative loss ratios, cumulative sum of IRRs will be use that in the for the loss reserving model. Now, first of all, I'm going to show you a few results and visualizations, and I'm going to show you a sample of 136 firm year, and we have a complete IRR function. So all the IRR are observed in all of the 10 lags and across the 1987 to 1999 in workers' compensation. Later, while we're developing a loss reserving model, we use a much larger size in order for us to train our data and validate. So I think across 1987 to 2010. But here I'm going to show you a sample of 136 function curves. So each curve represents a loss development in terms of the, on the left-hand side, the IOR. On the right-hand side, is the COR for one company in a particular year. So by observing that, you can see it's not quite heterogeneous within a line. You can sort of see a pattern in terms of the IOR, but we do observe a few anomalies. So like a few of these outliers, extremely large IORs to be concerned. Now, we're going to adopt a unsupervised learning to help us to gain more interpretation out of these functional curves and help us to study the anomalies and do the outlier detections. But first of all, let's look at this, just some summary statistics. The thing of interest for these workers' composition business, that's in the first two lags, 0 and 1. We can see the IOR in terms of mean or the median, it's pretty large compared to the rest of the lags. But when we can look at the future lags, the general pattern is the IOR slowly decreases. It's not decreasing to 0 right away. So it's a characteristics of the long tail business. And we do observe a lot more variation. So MAD here, median absolute deviation. So that's a robust of the influence of the outlier. So we can see that actually in lag 1, we have the most variations. And also in terms of median, it has the highest IOR. Also in lag 9. And we see unusually high. You can see it's pretty skewed, so we do have some significant outliers here. That's to keep in mind. So the unsupervised learning methodology we're going to adopt to learn these functional curves are mainly the principal component analysis, PCA. I guess most of you heard of that. And there are 3 main reasons we use this PCA. One, of course, for dimension reduction. It's great for exploring this data structure in high-dimensional functional data and produce a 2-dimensional visualization that can help us to learn the results. And it's great for the interpretation, as I'm going to show you some of the graphs of some of our results. And third, the PCA also in terms of machine learning is great for the feature extraction. And when I'm mentioning the loss development and loss reserving model in the end, you see we're again incorporating the PCA as part of the loss reserving model to help with the feature extraction. Now, in terms of the Pca algorithm we're using, we are adopting the Crookes-Moser Oliveira 2007, and that's a Pca grid algorithm, and that's a robust Pca algorithm. We're not saying this is the best or this is the only one you should use as a PCA, but in general, robust PCA, that's going to give us a better result under the influence of the outlier. As we can see, we have a few outlying observations. And the main result, the visualization we create Bivariate and functional backplot using the first 2 PCA scores. And that's inspired by the Heinemann and Shen 2010 paper. And they have the R package called the rainbow plot. And also the robust PCA algorithm, it's really easy to implement using R via the package. And in the end, we're going to show a few more visualizations that help us to track a company's loss development patterns over time. So let's see, right next, I'm going to show you the PCA results, again, from this 160 36 loss development curve samples. Now, you can see here, it's a biplot, basically explaining the IRR in each lag, how much influence they have on the principal component scores. Let me put on some visual aids. So these additional lines just visual aids, but for just for the visual aids. Now you can see only the lag 0 negatively influenced our first principal component factors. That's saying the points to the right of the 0 in the to the left to the 0 of the right of the x-axis. Right, they're likely to have a higher IRR in lag 0, especially the point in the lower left-hand side. On the opposite side, so we have an arrow pointing 9 and 7. So these two lags, the IRR in these two lags, in lag 7 and 9, positively influence PC1 and PC2. So all the points that's congregating here, they're likely to have a larger IRR in lag 7 and 9. Down here, where the arrow pointing 1, lag 1 excludes, will negatively influence PC2. That does not have much influence on PC1. So again, put in a visual aid, all the points are in line with this direction, likely to have a high IRR in lag 1. Now, through the plots, we can also explain sort of the correlations between the losses in two lags and help us to discover some patterns. So the lag 0 and lag 1, they have a really small angle. You can see that they both negatively influence the PC2. So they are somewhat positively correlated. So if an insurer has a high IRR in lag 0, likely it's accompanied by a high IRR in lag 1 and so on. And all these arrows that are bunching here, so all the lags in the middle, lag 2 to all the way to lag 8, excluding lag 7, they are all positively correlated. They tend to go up and down at the same time. Now, comparing the lag 0 and lag 9 in terms of the incremental loss ratio, you see the arrow is almost 180 degrees, and that suggests they are negatively correlated. Right? If the company has a high IRR in the initial lag, it's unlikely to have a high incremental loss ratio in the later lag, especially lag 9. Let's do the biplot from the PCA, so we can have some interpretable, good interpretation, just to get an idea of the general patterns. Our next visualization I'm going to show is the bivariate and functional backplots. So first of all, the bivariate backplots. So again, x-axis is the first principal component score. Y-axis is the second principal component score. The dot in the middle is right at 0, 0. And the inner circle here, which contains the middle 50% of the observation. The outer circle here, which is the 99% fence. Right, that's assuming if the data is bivariate normal distributed, it's supposed to fence 99% of the observations. But we can see that it's clear that our PCA score is clearly not bivariate normally distributed. So we have a bunch of outliers. We have almost 10% of the observations as the outliers here. Now let me put on a visual aid that I'm previously on. In terms of the biplots, you can see that, right, as we said, the points in the lower left-hand side of the region, they tend to have a high lag 0 ILR. Right here, high lag 1 ILR, and up here, high ILR in lag 7 and 9. So with the help of the bivariate backplots and the biplots, we can again help us visualize the patterns and detect some outliers and study the patterns of the loss development in this sample. Now we can, so this one shows the functional backplots on the right-hand side. It's basically the mapping from the bivariate backplot. The white line here shows the median development curves. Again, the median pattern is we have a high zero value in lag 0 and lag 1, with lag 1 being a bit higher, and it slowly decays over the time. Apologize for the wrong color matching, but the dark gray area is supposed to house the middle 50% of the observation, and the light gray means the 99% fence. And the outlying curves are pictured as the red. Now, again, remember in the bivariate backplot, we're saying that the observation on lower right or lower left-hand side tend to have a high lag 0 ILR, and these observations are exactly matched in the red circle are exactly matched to the functional backplot we see here. So they have an abnormally high incremental loss ratio in the first lag. Again, the green circle here, this observation is mapped to the functional backplot, which correspond to the green circle here. You see just a slightly higher than the 99% fence in terms of the IRR in lag 1. Again, the yellow circle here points to the abnormally high IRR in lag 9. Now, the following visualizations, as I said, we can use the PCA scores, and we can pick out single companies and track them over the time and see how they do. In this case, we picked 2 representative companies. It's coded as C12669 and C1463. Let me also put the visual aid on. So we can see the C1269, which from the year 1988 to 1999, it's in the solid red lines. It's traveling along the upper right corner, and with one observation that is being detected as the outliers, suggesting it's having a high lag 7 and 9 ILRs over the time. Compared to the other company, which is in the dashed line, C1463, you can see that it's traveling almost exclusively in the lower region. And it suggests it's been having a high lag 0 and lag 1 ILR over time. Let's put side by side by their actual functional development curves to make this illustration more clear. Right, so the first company on the right-hand side is the functional curve of the IRR for our C1269. So you can see that the outlier here, right, it's catching the high IRRs in the lag 9 here, and also for the other company in the year 1999, right, the curve in showing the high ILR in lag 1. Okay, so and using our function, we can track the incremental loss ratio over the years for any companies. And with the visual aid, we can quickly tell what's the general pattern of their loss development. Now we can also explore patterns within the company covariates as the second question. That's, for example, between the business with a company with different business focus, different capital structure, and situating in a different geographical area, do they have the similar or different loss development patterns? This one shows again the PCA plots PC1 versus PC2 by different business focus. A majority of the company here are classified as the commercial, are labeled as commercial companies. And you can see there are a few personal companies situating here. So you can see they're kind of situated in the different parts of the plot with the companies that's labeled as a commercial. So has a lower PC2 score, higher PC1 score. That may suggest their incremental loss ratio level is slightly higher compared to the company with the personal focus. And here, comparing the mutual and the stock company and the others. So for the others, we don't have many observations here, but comparing mutual and stock, they're actually sitting pretty close to each other. So we don't observe much difference in loss development patterns between the mutual and the stock companies here. And by the region, there are 6 regions to be comparing with. So, but let me put on the visual aid. You see here the red dots, the companies in the Midwest region situated right here compared to the companies, for example, in the Northeast region situated to the right, suggesting the Northeastern company may have a higher incremental loss ratio in terms of the level compared to the Midwestern companies. Oh, and let me go back. Right, so and we can also explore the patterns with even more company covariates and make visualizations in this 2-dimensional. So in short, the PCA technique help us again to explore the to loss development curves over the time and present it in the bivariate visualization. Now I have 5 minutes, so let me briefly talk about the loss reserving model we have in mind. Again, the goal is for us to forecast the partially complete in terms curves in terms of the cumulative loss ratio. And we ask ourselves if we can incorporate information from the past complete curves, right, which is above the triangles, and if we can incorporate information from the similar curves of the other companies. So we can borrow information, not relying on the information for our own company. So if we can borrow that. Now our thought and idea is closely related to a few functional data forecast methods. Here's 2 of them. One is in the econometric field by a paper of and Lee, 2006, and the other one it's by Hanling published in 2013. So they both study functional data and try to forecast them in the future. So Lee dealing with the treasury yield curves. So the main idea of the 2 works, so they model on the functional data and estimate a few parameters. In the Lee, they use a parametric modeling, applying the Nielsen-Siegel models with 3 parameters. They on the existing treasury yield curves in the training data and forecast the level, slope, and curvature parameters into the future and plug it back into the parametric model to recover the yield curve forecast. Hanling relies on the non-parametric modeling. He's dealing with the electricity demand curves. Now he's using PCA to extract features, forecast the PCA scores, and also recover the forecast using the PCA scores and the loadings. Now our approach will be similar to the Hanling because so electricity curves also dealing with the reporting delay, so partially complete curves. So we can use so it allows the forecast of the partially complete curves. Now that's briefly the idea. So we're going to also rely on the Pca decompositions on the complete CLR curves. By Pca decomposition, we'll be able to obtain the mean curves, loadings, and the Pca scores. Now we'll be forecasting on is the Pca scores. Now these scores and loading conveys the industry-wide information. And the forecast of the Pca scores will be depending on the covariates that we know. So for any type of the companies, it will obtain a specific forecast of the Pca scores. The next step is to forecast the incomplete portion of the CLR curve using the penalized least square. So the idea is we have an incomplete portion, either it's completed 9 lakh complete or just 1 lakh complete. We have the complete information. So we'll run it through a least square so we'll set up a least square on the partially complete curves, but subject to the regularization constraint. And the constraint will be based on the Pca score forecast obtained from the complete curves. In this model, there'll be 2 hyperparameters. So besides the regular shrinkage factor associated with the regularization models, and we will have the number of Pca loadings be able as another hyperparameters. And then we calculate then after forecasting a CLR, we recover the ultimate cumulative loss, obtain point estimates, and construct prediction intervals. So right now we're at, we have some initial results for the curve, for the forecast, and using the data provided by Ledger Investing over 20 plus years for many companies. And I can tell you the optimal model, after the cross validation, it always tells us the shrinkage factor is not 0. So so the past information, the Pca score forecast from the past complete curves do convey some useful informations. The number of Pca loadings picked that varies. For some cases, we have the model picking 3 Pca loadings. In some cases, just picking 1 Pca loadings for the final modeling. Right? I think that's all the time that I have. So basically, quick conclusion: we apply the statistical learning method to traditional insurance data. And we try to explore and detect some development patterns industry-wide and among the company covariates. We propose a loss reserve model based on the non-parametric functional forecast, and we are continue this development. All right, thanks.